Okay, so section 1.7 deals with linear independence. This is a very important concept in linear algebra. And I haven't even given you the definition yet for linear independence. I'm just going to show you two vectors, and I'm going to ask you, do you think these vectors are linearly independent? All right, I'll give you a moment to copy it down. Okay, so I'm hearing some good responses here. Many people are saying no. Noah says that one vector is a scalar multiple of the other vector. So the fact that means there's a connection between the two vectors. The fact that the second vector is twice the first vector, v2 is twice v1, means that these vectors are not linearly independent. Okay. That's right, Binyam. If you were to graph these two vectors, they would fall on the same line. Absolutely. And remember in your notes now, when you have V1, you should write it in your notes as V1 with the little arrow symbol above it. Okay, so let's get to the solution. We'll be a little bit more formal here. Okay, everybody's good. Move to the solution here. So since the second vector is equal to twice the first vector, we say the set of vectors, v1, v2, are linearly dependent. The set is a linearly dependent set. Okay. But another way to look at it is if you were to, well, hold on. Okay, so if you were to think about the vector equation, x1 times v1 plus x2 times v2 equals the zero vector, you would see then, I mean, saying that the second vector is twice the first vector is equivalent to saying that -2 times the first vector plus, hold on here, this statement here that v2, the second vector, equals twice the first vector is equivalent to saying that -2 times the first vector plus the second vector is equal to the 0 vector. That means then that if we write down the vector equation x1 v1 plus x2 v2 equals 0, then x1 is -2 and x2 is 1. And this is what's called, that's a non-trivial solution to this vector equation. A trivial solution would be if x1 and x2 were both 0. That's called the trivial solution. But we ended up getting a non-trivial solution. Okay, so there's a trivial solution would be if the x1 and x2 coefficients were both 0. That's called the trivial solution. In other words, the solution x1, x2 is 0, 0. That's called the trivial solution. Anything else is a non-trivial solution. All right, you're welcome. You're welcome. Now, what I want to do is bring up a page in your lay textbook here. So, may I move into the textbook? Is anybody okay? All right. So if you go in your ebook in section 1.7, there's a definition for linear independence and linear dependence. Let's see, Samuel says about a screenshot. Well, yeah, I didn't think about that, but I'll, oh, you're saying, okay. All right, Moshe, you're good? All right, great. All right, so let me go in here to, let me see. Hold on. One moment here. Yep, this is what I want. Okay, can everybody see the textbook well here? All right, great. So, let me see here. Maybe I can load this up a little bit. Hey, all right. Okay, so this is the definition of linear independence and linear dependence, and it's one of the most important definitions you're gonna see in this course. If you have a vector, this first vector equation, okay, this first vector equation, if the only solution is the trivial solution, meaning that x1, x2 up to xp is all zeros, then the set of vectors are linearly independent. On the other hand, the vectors will be linearly dependent if the weights, and they call them weights, C1, C2, Cp, but they could just as well call it in the second equation there, they could call it, instead of C's, they could call it x1, x2 up to xp. If you get a non-trivial solution, then you have linearly dependence. You have a linear dependent set. And then you have a linear dependence relationship. Basically, that means that every variable can be expressed as a linear every vector can be expressed as a linear combination of the other vectors. There's a connection. So let's look at another example here. Let me well, yeah, I think Solomon, I don't want to give, I mean, what I say is there isn't going to be, okay, take a moment to write it down. Okay, that's fine, that's fine. So Moshe says there's only a trivial solution. Right, when you only have the trivial solution, that's when the vectors, the set of vectors, will be linearly independent. So there's a lot of ways you can construct problems. A lot of ways that you can construct problems. Okay, so Solomon, I'm going to bring this definition back up. Okay, I promise. But let me get to the next example. I want to give people, okay, a little time to work on that, work on some classwork. Let me get to this, just one more example here. Okay. Okay, so hold on before you copy that. Let me just. Yeah, we'll go with this. Are these vectors linearly independent? So the first example, you were able to sort of, you could intuitively see it. This example might be harder to intuitively see. But we know what we need to do. We know what we need to do. We need to start with the definition. Well, we need to what do we need to write in order to test for linear independence of vectors? What kind of equation do we need to write down? That's right, Matthew. We need to write down a vector equation. Okay. Okay, and actually, that's right. That's right. It would be a vector equation, and as Mikhail says, it would be a homogeneous one. All right. So, may I go to the next page? Are we okay? All right. Thank you. So, okay. Here's the, the $30,000 question, right? Does this vector equation have only the trivial solution? Trivial solution would be x1, x2, x3, all e being 0. So we need to solve the vector equation. Now, I mean, I think this is easy enough to do by hand. I'll certainly on the exam want to see a lot of row operations by hand, and all the ones that where you can use the MATLAB, I'll let you know. But this one, if you want, you could try to put it in MATLAB. and see what you get if you want, just so you practice MATLAB a little bit. So from the vector equation comes our system. From the vector equation comes our system of equations. Indeed, you will, Binyam. There will be a free variable here, I think. And then from the system of equations comes your augmented matrix. Okay. Are there any questions so far? All right. May I move to the next page? I want to make sure I'm going at a decent pace here, because I know you're copying notes. All right. Does anybody need a little more time to copy? Thank you, Michael. Thank you, Matthew. It's okay if you do. Okay. Well, then let's move to the other thing here. Thank you. It may be shown then that, so I didn't do all the row operations. I just, worked it out, and I want to save you from save time here on the notes. So the augmented matrix would be this. Did anybody get this? Try this in MATLAB and get that augmented matrix? Okay, Binyam, very good. All right, and so naturally, we have a free variable, and x2 is negative x3, x1 is 2x3. Well, this is a non-trivial solution. Now, x3, if we set it equal to 0, then x2 and x1 will be 0. But the thing is, you can set x3 equal to a different number, and you'll get a different solution than 0, 0, 0. So it's a non-trivial solution. Non-trivial. Therefore, this set of vectors is linearly dependent. So as an example, if you were to set x3 equal 5, then x1 would be 10. If x3 were equal to 5, just for example, then x1 would have to be 10 and x2 would have to be negative 5. And therefore, 10 times the first vector minus 5 times the second vector plus 5 times the third vector would equal the 0 vector. But how I like to think of it is, that's true. But whenever I think of linear dependence, I think, okay, like one of the vectors in the set can be written as a linear combination of the other vectors. There's a connection. One of the vectors in the set can be written as a linear combination of the other vectors. Okay, there's a linear dependence relationship then among the vectors. Okay, and that's actually relates to Theorem 7 in your textbook from section 1.7. That relates to Theorem 7, that comment I just made. So like for instance, for our little vector equation here, 10v1 minus 5v2 plus 5v3 equals 0, well, I could solve that for v1. v1 then would be equal, it turns out, to a half v2 minus a half v3. So Solomon, don't worry about disconnected. It's going to be on the recording. But basically, we're just you know, working through the solution here. This is going to happen, you know, class. So this is another reason why I guess I'm glad I'm recording the lectures, because sometimes students do get disconnected. It just happens, you know. But what we did, Solomon, was we took that vector equation from the linear dependent we took our vector equation to test for linear dependence and wrote out the augmented matrix and then solved it, and we ended up getting a non-trivial solution. And so therefore, the set of vectors v1, v2, v3 is linearly dependent. And again, you know, I like to, when I think of that, I like to think, okay, well, gee, one of the vectors must be able to be written as a linear combination of the other two. You know, so like this, to me, this this here, this vector equation is a little abstract to me. But saying that one of the vectors can be written as a linear combination of the other vectors, v1 equals a half v2 minus a half v3, makes me think, okay, these vectors are linearly dependent because one of the vectors is connected to the other two. There's a dependence relationship. Does that, how many kind of like it? How many does it help writing v1 as a linear combination of v2 and v3? How many of you kind of help? How many of you does that help you feel what we're talking about when we say linear dependence? Does that help you, maybe give you an intuitive feel? In other words, what I'm saying is this. Thank you, Mikkel. Thank you, Samuel. There are two statements here that support linear dependence. And I'm saying the second, even though the first statement is standard, to me the second statement helps me just feel the linear dependence intuitively better. And Mikkel and Samuel agree, and I'm happy with that. Are there any questions?